Hi and welcome back to Biostat Squid. In the last few videos we talked about survival analysis, log-rank test and Cox regression. Now it's time to put all that theory into practice and do survival analysis in R. In this tutorial we will learn how to do a complete survival analysis, including plotting a Kaplan Meier curve, testing for differences using the log-rank test, building a survival model with Cox regression, and visualizing our results with a forest plot. We will use the R packages survival, ggsurvplot, and survminer, as well as the tidyverse to do this. So go ahead and install those libraries. And as always, you can find the code I'm using in this tutorial at biostatsquid.com, where you will also find a step-by-step explanation of the code. For this tutorial, you will need R or Rstudio. You will need to install the packages we mentioned earlier, and we will use sample data from the package survival. So if you don't have a data set to play around with, you can totally follow this tutorial. So if you're ready, let's dive in. Great, so for those of you who already watch my other tutorials, you know I like to clean my environment up in case I have hidden objects in the background. I free up memory and I set our working directory. We also need to load the necessary libraries. I will set seed. It's not necessary, but I always like to do it at the beginning of all my scripts in case I use random steps. And as I was saying, let's load the relevant libraries. So that's tidyverse for data manipulation and so on. And then our three packages we will use for our survival analysis. Great, so as we saw in my previous video about ggplot tips and tricks, I also like to set a general theme which I can use for all my plots. But this step is not necessary and you can totally use one of the ggplot themes. Right. So let's start by loading the data. So the data set we're going to use today is part of the survival package and it's called Rotterdam. So we're just going to give it or assign it to this object, df, and we can learn more by calling Rotterdam. We can learn a bit more about this data set. So it's a breast cancer data set. And we have information about the different columns. There's a patient identifier, year of surgery, the age at surgery. There's different data for each of the patients, the differentiation grade, the size of the tumor, and so on. So that's all the information about our data set, and we can go back to it when we need it. Great, so let's have a look. This is our data set. These are our columns, and we've got almost 3,000 patients and 15 different variables. So we can also call call names to get the name of the columns. Great, so there are two key columns we need for survival analysis. The first one is the censoring status, whether the patient was censored or not, and the second is time to event. So let's start by looking at the censoring status. We need a column that has 1 if the event happened and 0 if the event was or the patient was censored. You can also use true and false, but let's go with 1s and 0s. So we are going to take death as our event, and we see that this dataset already has the column death. So we can quickly check. There you go. So there's just 1s and 0s in this column. So since the values are already coded with 1s and 0s, I will just create a new column called status that will be identical to death. And now if I called head df, now we have the column status, which will be our censoring status. Now, if this were not the case, if you didn't have this column already, you could easily add an if-else statement or use the tidyverse function recode to recode your values into ones and zeros. Great, so we can have a look at how many patients are censored or not with table. So we have almost 1,200 patients that are censored and 700 are not. Great, so that's step number 1. Step number 2 is the time to event. So in this data set, we can either use time till death, or our relapse time till relapse. So I'm going to use time till relapse, but in your case, you might have a different event. And let's first have a look at our column. So I just printed the first couple of values and we see that the numbers are very big, and that's because our relapse time is in days, which we also see here, days till relapse. So let's just convert it to years. Let's have a look. And now we have our relapse time or time till relapse in years. Nice. So now that we have our 2 essential columns, we can start our analysis. And the first step is to create a survival object. So that's what we're going to do. Survival object. And we use the survival function. And we need to pass the time and the event. So again, our column time, we decided we would go for relapse. So our time in years. And then our event is basically our censoring status. So that's status. There you go. So that is it. This is our survival object. And if we see hit, survival object, you see we get a vector of the follow-up time, and these pluses just represent if an observation or a patient was right censored. In this video, we'll only talk about right censoring. Okay, so next step is to create a survival curve with the function survfit. This is the syntax, so I'll show you in a minute. Survfit, serve object, and we need this squiggly line, which always takes me ages to find. There you go. And we have 1 because for now we have no groups. We're not grouping our data or comparing 2 groups. And our data is df, right? So we're going to assign this to an object called s1. This is our survival object. I'll just move this up here because we haven't actually created the survival curve yet. So we can get a summary for this. I think I haven't. Did I run it? Yeah, I did. There you go. So this is our survival curve data. But how can we actually plot it? Well, the answer, of course, is a Kaplan Meier plot. And we can do it really easily with ggsurvplot. So I'll just show you. ggsurvplot. And if you ever want more information about how to use a function, you can always use this. Not that, you can always use this. And this will give you the details of the actual function and what you need and so on. So ggsurvplot is our function, and we just need to pass on the survival object. We will set a line width of 1, for example. We can also edit the labs, the titles for the X and Y axis. So my X axis is going to have years, and my Y axis is going to have overall survival. Perfect. So this is basically it. This will already give you a nice Kaplan Meier curve. Of course, you can customize it. We can add confidence intervals. For example, we can add a risk table, which might be informative. So now there's a risk table with the different survival or the different risk at different time points. We can also use scale, ggsurvplot, which will scale it. And now it's nice because we see the overall survival at 50% to 100% and so on, which might be interesting, for example, for metrics like median survival time, right? And this is just, you can treat it as a ggplot object, so you can edit it, for example, with a theme. I'm going to use my biostat squid theme, for example. You can use different other ggplot themes. We can also use scored Cartesian to just show, for example, time from 0 to 8 years. So it's totally customizable. And we can assign this to an object and then save that object if we wanted to. Save it to a PNG object or whatever. Nice. So you're probably trying to answer certain questions with your data. For example, estimating survival after a certain number of years. So that's a very easy question to answer in R. So if we wanted to know the probability of surviving beyond a certain number of years, we can do this with the function summary. So I'm going to call summary, and then I use my object, my survival object, and I pass on 1 for 1 year. And then I just need to call surv. This will give me the probability of surviving beyond 1 year. You can also chance different times by passing on a vector. For example, 0, 0.5, 2, 5, 7, and this will return all the different probabilities. And if we check our Kaplan Meier curve, for example, the survival probability at 5 years, if we go up here, is exactly that. Where is it? Around 63%. We can actually quickly check. I'm going to draw a line, a vertical line with the x-intercept at 1 year, line type dashed. I'm going to paint it color red, and my size is going to be 1. And now I'm going to draw a horizontal line as well. And this time I'm going to copy all of this, but this time I need the y-intercept, which is going to be my probability at time 5, at year 5. So this is basically what we had up here, but just at time 5, right? And then let's just use scored Cartesian. Oh, we have it above, right? So that's perfect. Let's have a look. Whoops, the x-intercept should be 5 years. There you go. So now we know that the probability of not relapsing for 5 years or more is around 63%. Great. So another thing that we can do is to estimate the median survival time. And we can do that very easily by just calling our survival object And here we can see the median survival time is 11 years. So that's pretty nice. That's very easy. And you can, of course, also add it to the plot, highlight it maybe with a dot or a horizontal and a vertical line. There are many different options. Okay, so imagine we want to test whether there is a difference in survival times between patients who received chemo or not. So this is the basis of the log-rank test, right? Comparing groups, as we saw in the previous video on the log-rank test. So let's just first have a look at our column chemo. So if we remember, there is a column in our dataset called chemo, which has 0 if the patient did not receive chemo and 1 if the patient did receive chemo. And we can get a nice summary of the numbers with chemo. Nice. So we see that more than 2,000 patients had no chemo and around 500 patients did have chemotherapy. Right, so to compare two groups, we do it similar as we did before. This time I'm going to create the object S2. So we use the function survfit and we take our survival object. We can take the same survival object we built before, but this time we will add this squiggly line, there it is, and we will have the name of our column of interest, chemo. And don't forget that our data is called df. There you go. So now we have our second object, and we can, of course, plot a Kaplan Meier curve. So to do this time we're going to use the ggsurvplot function, which gives us additional functions or additional ways of editing it and customizing it. So the function is this, ggsurvplot, and again we can have a look at all the options, ggsurvplot, by calling the question mark. So I want, okay, so you have the different options here, and as you can see, there are many more ways of customizing it, so it might be a better option. So you need first your fit. So this is the model we fit, which is, you know, taking into account the different groups marked by the chemotherapy column. Then we have to give it our data set. This is important if we don't want to get weird error messages, so you need to specify the data set you're taking it from. Now we're going to add line size of 1. We can actually add a custom palette. So I'm going to choose two colors, orange and green, for example. You can, of course, also add the codes if you want. So for example, I have one here, which is E7B800. So that's my orange. And for example, 2E9FDF. So that's a blue. Nice. So that's my custom palette for the two groups. Then we can actually decide what shape we want our censored observations to be. So I want it to be, there you go, the vertical line. And we can choose the size as well. So I'm going to choose size 4. We can add confidence intervals. We can add a p-value. We can add a risk table, for example. We can actually edit the risks table to have different colors. And we can also change the legend labs. So that's the name of the different groups. So for example, I want the group called 0 to be called no chemo, and the group called 1 to be called chemo. Chemo. Perfect. We can, I don't know, there are many different things you can customize. So I like to say the height of my risks table to 0.25. This might be useful to change if you have multiple groups. It might, you know, compress the plot a bit. And we can, of course, add a theme. So for example, it even has an option to add it here, GG theme. So I'm going to add a theme black and white, for example. So let's have a look. Let's see if this works. Hopefully it does. Let's see. There you go. So this is our plot. I can zoom it in so you can see. And it's, yeah, a much nicer plot than before. You can, of course, customize everything, make the titles bold, the axis labels bigger. Nice. So now we can compute to actually test the difference between these curves, right? Because they seem quite similar. So are they actually statistically different? Is there actually a statistical difference between the survival times, in this case it's relapse, between patients who received chemotherapy versus patients who didn't? And we do this with the function survdiff. So that's the function to perform the log rank test. So log rank results for chemotherapy, that's going to be the survdiff function, and we just need to give it our object. So I'm going to repeat the stuff here, and then we have the squiggly line, chemo, and data df. I think it should work if you pass on S2, but just in case I typed everything. And these are our results. So let's have a look at the results. Nice, so we have our two groups, no chemo and chemo. So we have the number of events. We have the number of observed events. This is after censoring, and the number of expected events. And as we talked about, it's based on a chi-square test, essentially. So the p-value of 0.4, since it's much bigger than 0.05, which would be our significance threshold, means that there is not a significant difference between getting chemotherapy or not. But perhaps we can try hormonal treatment. Let's copy this and let's try hormonal treatment. And instead of this, I forgot what was the name of the column. Hormonal treatment, there you go, hormone. So that's if the patients received hormonal treatment or not. So let's chance that. And the p-value is really low. It's lower than 0.05. So it seems like there is a statistically significant difference in the survival probabilities between patients who received hormonal treatment and patients who didn't. Nice. So to end this tutorial, let's talk about Cox regression, right? Because log rank test lets us compare two different groups, but it doesn't let us add other covariates that may influence survival time. So for example, here we were comparing patients who received chemotherapy or didn't, but we didn't, for example, take into account the size of the tumor and stuff like that, right? So Cox regression analysis allows us to fit a model with many covariates that we think may influence the survival time. To fit a Cox regression model, we just need to call the Cox function. So this is our function, and then I'll just copy the same thing as before. Let us see. And I'll take the squiggly line because it always takes me ages to find it. There we go. And now we can add as many columns as we want because we're fitting any variable we want, right? So I'm just going to add all of them. But of course you can select and choose the variables you think may influence survival time. Menopause and grade and age. And don't forget to add your data at the very end. So this should work. I'm going to assign this to Cox results. Let's see. Yes. Okay, so now we have our Cox results here. Let's have a look at what they will show us. Nice, so this is how it looks, right? So these are the results. We have all our columns here, right? The coefficients, the exponentiated coefficients, which, if you remember, are just the hazard ratios, the standard error, and the z-score, and then the p-value, right? This is really the column we should be looking at, the hazard ratios, to get a more direct interpretation of how each variable influences survival time. And the thing is that for each of these groups we're comparing the presence versus the absence of a certain variable. So for example, with chemo, we had group chemo equals 0, which hadn't had chemotherapy. So I'll just show you. So we have the values 0 and 1. So 0 didn't have chemotherapy, 1 did. And it's the same with most of them, I think. So hormonal treatment is more of the same. 0 if they didn't receive it, 1 if they did. So we're always comparing the group that did have that in reference to the group that didn't. Right? So if we have a look and check table, we see that there's around 2,600 patients who didn't receive hormonal treatment versus around 300 who did. So the coefficient here in hormonal treatment, where is it? Over here, it refers to the change in the log hazard rate of having the treatment compared to not having it. In other words, the group of no hormonal treatment is our reference. For size, however, there are 3 groups. If we have a look, size, there we go. So we have 3 distinct groups. So the model took the first group, tumor size lower than 20, as a reference. And then we have the coefficients for the other 2 groups, right? So what if we wanted to change this? For example, I'll make up a column called treatment, and I'll make it really dumb. For example, I'll just give half of the patients drug A. So treatment, and I'll give half of I'll just repeat the values drug A and placebo, for example. So DF treatment is a very stupid column with half the patients having received drug A, half the patients haven't received placebo. But what I wanted to show you is that if we now build Cox regression, I'm just going to take hormonal treatment and treatment, the new column, data equals df. So I'm going to build a very simple Cox regression results. I'm just going to name it 2, just to not confuse things. So these are our Cox regression results. So now we have treatment, placebo. So actually our drug A is our reference. So drug A is the reference for this comparison. But usually we want to see how drug A improves or worsens survival time compared to the placebo. So if we wanted placebo to be the reference group, we just need to make a column factor. So DF treatment. We'll use factor to make the treatment column a factor with levels drug A and placebo. There we go. We'll just run this. And now we can re-level this factor level. So if you see now, class DF treatment is a factor. And now we can re-level it with re-level, and we use treatment, and we set the reference to placebo. So now if we call unique DF treatment, we see that placebo actually comes first, and it's the reference. So now let's run this again. This Cox regression 2. And now we see that placebo is the reference, and we're seeing the hazard ratio of drug A compared to the placebo. So that's a nice trick to know. So I'm just going to get rid of this dummy column. Great. So now we can also get a summary of the model. So we can get the confidence intervals of the estimated hazard ratios and the different test scores of our Cox results. And this is basically all the information we need. And in the Cox regression video, we mentioned that before interpreting the results of Cox regression, we need to verify whether the proportional hazards assumptions are respected. So the Cox model assumes that the hazard ratio between two groups remains constant over time. And we can test this very easily with this function, which tests for the proportional hazards assumption based on these Schoenfeld residuals. So I won't go into details, but what you need to know to interpret the results is that the lower the p-value, so if you get a p-value of lower than 0.05, then there is actual evidence against the proportional hazards assumption. So the hazard ratios are not constant over time. And if you get a chi-square test statistic that's very high, it means the higher it is, it means the stronger the violation of the assumptions. So we're just going to quickly test if our variables follow or violate the proportional hazards assumption. And we use the survival function, this one. So we just pass the Cox results to this function, and this will give us the test, right? So these are all our variables, and for each of them we will have the chi-squared statistic and the p-value. So we see that some of the variables, for example ER, PGR, which I think are the estrogen and progesterone receptors, age, and so on, have very low p-values, which means that maybe Cox regression isn't the best option because many of these covariates have hazard ratios that are not constant over time. We can also plot the Schoenfeld residuals over time for each covariate, and we do this with the survminer function, gg. Let me see if I find it. This one. It's a lot of consonants. So we pass on the test, and we can have a point size of 0.1 to make it a bit smaller. So these are the Schoenfeld residuals, and yeah, they're not the prettiest plots, but how do we actually interpret this? Well, basically, if we see no pattern, then if the residuals are like scattered around 0 with no clear trend or pattern, this suggests that the proportional hazards assumptions is reasonable. So that's good. The residuals are constant. In any case, we see the p-value is very high, so this would be kind of very kind of stable or no pattern, right? If there is a linear trend, either increasing or decreasing in the residuals over time, that might suggest a violation of the proportional hazards assumption. For example, if the residuals are consistently positive or negative across time, it indicates a time-dependent effect. So we see this, for example, I would say here, we see that it tends to go down. It seems like as time passes, the residuals tend to accumulate like in the lower part, so negative values. And then if you see like a non-linear pattern, like a U shape or a V shape, that also may indicate deviations from proportional hazards. So yeah, they're not the easiest plots to interpret. So, but the p-values are there to help you and to help you find which variables violate the proportional hazards assumption. Nice. And perhaps one last thing about the Schoenfeld residuals. If you see parallelism, so if you see that the spread is relatively constant over time, then it means the residuals are more or less constant over time. But if they widen or narrow over time, for example, in this case, they seem to be narrowing over time, then that may suggest a violation of the assumption. Okay, so I promise this is the last thing about the Schoenfeld residuals. Let's move on. Let's get a summary of our model with summary Cox regression. I think we did all that already. So this is our summary, right? So for example, we see that for hormonal treatment, the exponentiated coefficient is 0.79. So that's the hazard ratio. So if we hold all the other variables constant, patients who get hormonal treatment have a decrease in the risk of death, or actually relapse, of 21%. So that's 1 minus 0.78. And size, it seems there's a positive association between the size of the tumor and mortality or relapse. So it's 2.33 if the size of the tumor is bigger than 50 millimeters, if we compare it to a size lower than 20. So finally, a very nice way to visualize the hazard ratios is with a forest plot. And we can do that very easily with the function ggforest. We just need to give it our Cox results and then the data. So this is our forest plot. Again, it's a ggplot object, so you can edit almost everything. And let's have a look. Zoom in. This is what it looks like. So in the x-axis, we have the hazard ratios. Remember, 1 means there's no difference between the value and the reference. And a higher one, a higher hazard ratio means that it increases the hazard ratio of the event. So in this case, relapse. And a lower hazard ratio, lower than 1, means it actually decreases. It looks like most of the variables in our dataset increase the hazard ratio of the event. We have here our p-values and asterisks indicating if there is a significant difference or not. And yeah, this is a very nice way of visualizing our hazard ratios. So that is it for today. Thank you very much for watching. If you're new here, don't forget to subscribe. Let me know what you thought of this tutorial. I really hope it was helpful, and I really appreciate all your comments and support. So thank you very much. Have a squid-tastic day and see you in the next one. Perhaps you only have the start time, for example, the surgery date, and the day of last follow-up. But you don't have the actual duration since the start time to the end time. But remember that for survival time analysis, we need the actual duration from the start of the event till the end, when the event happened or the patient was censored. So I'll just make up a quick example to show you how you could calculate time to event from dates. So I'm just going to assign this to a df2. And I'm going to create a quick data frame with surgery date. I'm going to take a sample from, I don't know, 1999. Let's have it by day. And let's take maybe 12 observations. And now we'll have another similar column. Let's see. That's going to be called the day of last follow-up. And I'm going to have dates from 2000 till 2020. So this is just a quick example. And if I call head, this is kind of what you would have, perhaps the start date and the end date. So I'll just quickly call class. So you see that surgery date. Where is it? There you go. It's not here because it's df2. So surgery date is of class date. And a very easy way to get the duration is to use the function asDuration and then wrap it up with the function asNumeric, where you can specify if you want the duration in years, months, or days. So I'm going to quickly show you how to do this. We're going to use the mutate function to create a new column, and imagine I want overall survival in years. So I'm going to have it in years. So again, I just call asDuration, and I take the day of last follow-up minus the surgery date, and I want it in years. But before that, I need to wrap it up with asNumeric. Where is it? There you go. asNumeric. So that it stops being a date and it becomes a number. So if we now call head df2, it's not there because I wrote mutate instead of mutate. There you go. So this would be our overall survival in years, and it does the calculations for you. And if you want it in days, it's as easy as changing years to days. So for example, I would have it in days. You can have it in months, whichever you want. So this would be my overall survival in days. So that's a nice trick if you ever have like the start date and the end date, but you don't have the actual duration.